So in this section, we're dealing with infinite series. So we're summing sequences, usually to infinity. Okay, I think they're all to infinity because this is a calculus course. Sometimes you might want to do a summation from 1 to 100. But a lot of what we're going to be doing is something like this: n over n plus 3. We want to analyze this series, right? We're adding up all the numbers in this sequence, n over n plus 3. So one trick we have up our sleeve is to calculate something called a partial sum. And a partial sum is when I think your text uses this notation, S sub 3. That means you just add up the first 3 terms of the sequence. So if I plug in 1 in for n, I get 1 over 4. If I plug in 2 in for n, I get 2 over 5. And if I plug in 3 in for n, I get 3 over 6. And then you just need to get common denominators, add those up, and then you get yourself a partial sum. So we do partial sums to give ourselves a kind of sneak peek into our investigation. Does this thing converge to one number? Does it diverge? So with this sequence, I'm looking at the numbers I'm adding, right? I've got 1 over 4 plus 2 over 5 plus 3 over 6. The fractions I'm adding are getting larger and larger, right? So if the terms keep getting larger and larger, that gives me an intuition that maybe this thing doesn't converge to one number because we keep adding more and more numbers as we go to infinity. Okay, so that's what a partial sum can do for you. We looked at geometric sequences before, so now we're going to study geometric series. And a geometric series is just when you sum a certain amount of terms in a geometric sequence. So we get a times r to the n minus 1. That's our geometric sequence, and we're summing it. And we're adding up a bunch of terms. That means we have a series on our hands. And if you plug in 1, you get a. If you plug in n equals 2, you get a times r. If you plug in n equals 3, you get a times r to the second power, etc. Okay. So let's see what else if we have a geometric series, the next logical thing I think to talk about would be what happens with it, as we go to infinity. It's got two options. It could converge or it could diverge, right? So if it converges, we're interested in it because then we can maybe find out what the value is that it converges to, and that can help us, evaluate some sort of real-world problem where we've got a series going on. And if it diverges, it doesn't come to one number. It keeps increasing and never stops going towards infinity, or it could be decreasing, going towards negative infinity. But either way, here's the rules. If it's a geometric series, it's going to converge if the absolute value of r is less than 1. And so just think about that real quick. The absolute value, so this could be negative 2/3, right? That's less than 1, or it could be positive 2/3. The reason why, the intuition behind this is that if you have like 2/3 or 3/4 or some number less than 1 for r, then every term is getting multiplied by a fraction. And the fraction is actually getting smaller and smaller, right? Because let's say r was 2/3. Then 2/3 squared is 4/9. That's smaller than 2/3. And then 2/3 to the third power, that's even smaller. The terms of the sequence are getting smaller and smaller. So the terms of the series are getting smaller and smaller that you're adding up. You're adding up smaller and smaller numbers. Eventually you're going to be adding something that gets infinitely close to 0. Now it says that there wasn't a greater than symbol, right? The absolute value of r, if that's greater than or equal to 1, sorry, I should have wrote this converges. And if the absolute value of r is greater than or equal to 1, then it diverges. Okay? Before we move on and talk about why we have to have this greater than or equal to symbol here, if it converges, if it's a geometric sequence, they follow a nice pattern every time, we can say that the sum from n equals 1 to infinity of a geometric series that converges is going to be, here's the geometric series. The sum is going to be equal to just a, that starting term, over 1 minus r. So you can just plug in r, plug in a, and then that's going to be the number that it converges to. So I put another type of series on the board here. A harmonic series. It's a particular type of series when it's just the fraction 1 over n, summed from n equals 1 to infinity. The book will give you a nice discussion on why that's divergent. That one's pretty interesting because the fractions are getting smaller and smaller every time, right? But that is divergent. Let's see. What else? Maybe the last topic here before we end this video. Telescoping series. And so a telescoping series, let's look at an example. A telescoping series is when you start looking at a good big list of the partial sums, you start seeing that every term of the series are having fractions cancel out. They're having terms cancel out. So here's an example. The sum from n equals 1 to infinity of 1 over n times n plus 1. And a lot of the time, it's going to be easier if you look at this by thinking about how it can be broken down. So we're going back to partial fractions that we worked on earlier in the course. This is the same as the sum of 1 over n minus 1 over n plus 1. When we break it down like that, then we can see two separate terms when n equals 1. When n equals 2, there's also two separate terms. So let's start looking at that partial series. If we plug in n equals 1, we get 1 over 1 minus 1 over 2. This is when n equals 1. And then when you plug in n equals 2, you get 1 over 2 minus 1 over 3. And then that's n equals 2. If you plug in n equals 3, you get 1 over 3 minus 1 over 4. And then it keeps going, right? So I stop there just so we can see the pattern. You might want to go a little bit more just to convince yourself. But check out these first two parentheses. We got negative 1/2, and that's eventually going to add to positive 1/2. Those two are going to cancel out with one another. And then in the second parentheses, we've got negative 1/3 plus 1/3. Those are going to cancel out. And if we were to keep going, this pattern is going to continue. We've got negative 1/4, and then a 1/4 will cancel out. So, using your imagination, as n goes to infinity, we never stop having terms, but whatever fraction is left over after your last cancellation is getting smaller and smaller. That's approaching infinity. Right? So this is an example of analyzing a telescoping series. This converges, and it converges to the value of 1, because that's the only term that's going to be left over after you make all that cancellation happen. Okay, so quite a few new pieces of terminology coming at you this week. I'll go make some videos for particular problems you're going to see in your homework.